I was asked to give about a 10-minute introduction regarding the preclinical models. So I'm just going to take a little bit of time to go over the mouse models that have been developed and well used that actually probably everyone's very familiar with. But this is supposed to be for continuing medical education. But that will also lead me into what our speakers today are going to talk about and how they're utilizing some of those mouse models. So this is a pathway that Mignon spent a fair amount of time earlier going over, so I won't dwell on it. I was glad to see Mignon's talk because I wasn't really sure where to put Sybil in this diagram, and she just had it kind of plopped in at the bottom, so that's what I did. But the point is that, as we all know, in addition to the JMML, many of these genes are also mutated in congenital disorders, which is very interesting. But the main genes, obviously, in JMML is the SHP2, is the NF1, which is a loss of function, the SHP2 gain of function, and the RAS gain of functions, and now the Sybil gain of functions. And basically, historically, these animal models have been developed as these genes have been discovered to be mutated in JMML. So one of the first reports was from Ben, and this was an animal model that bears a conditional knock-in of KRAS with a mutation at G12D. And this is just the basic studies from that manuscript. And the upper left panel here, because now my pointer's not working real well, this is just colony assays in response to increasing doses of GM-CSF. And the open circles are the cells in which the mutant allele has been induced, and obviously hyperproliferate compared to the cells in which they don't. The second panel over to the right demonstrates that the RAS GTP is higher, which would be anticipated. And then below is the in vivo studies showing that, I'm going to use this, are the in vivo studies showing that the wild type mice, or mice in which there's no MX1 CRE and therefore no induction of the mutant allele, survive fairly well, while mice bearing the induction of the mutant allele die off fairly quickly. And these mice also demonstrated splenomegaly. So really a good example, or a good model of KRAS-induced myeloproliferative disorder. A second model also came from Kevin Shannon's lab, and this included a conditional inactivation of NF1, and again, very similar phenotype, where, again, in response to increasing doses of GM-CSF, the number of colonies is greater in the mice bearing the mutant allele, or where in this case, where the NF1 has been knocked out, compared to wild-type cells. And again, these mice also develop splenomegaly, which is shown here graphically, as well as some basic histology here. And again, these mice did not die quite as quickly, but when the NF1 was deleted, these mice had a increased mortality compared to mice that had the wild-type NF1 alleles. And again, these mice in which NF1 had been knocked out had higher levels of activated RAS compared to the wild-type mice. So again, a very solid model of myeloproliferative disorder. And then one of the last models, and I believe these figures are actually from the Cancer Cell paper, which is 2005, but Gordon published this year in Blood a formal conditional knock-in of the D61Y allele, and the data very nicely recapitulated what was observed in this model, which was more of a transplant model. And again, these are the activating SHP2 mutants, where cells that had been transduced with wild-type SHP2 and then transplanted, the mice did fine. However, mice that were transplanted with mutant SHP2 expressing cells succumbed to disease. And again, these mice demonstrated splenomegaly as well. Looking at their peripheral blood counts, these mice showed increased neutrophilia compared to their wild-type counterparts, as well as increased peripheral monocytes. And in some of the biochemistry that was addressed in these studies that relates to some of the other work that's been discussed at length today, bone marrow cells from these transplanted mice demonstrated hyperactivated levels of phospho-STAT5. And again, as I mentioned, a second model has just very recently been published, which has been very useful to several of us, that very similarly recapitulated this data. And another of interest to me, based on my interest in this differentiation abnormality that I observed in looking through all these papers, is that all of the models very nicely show this expansion of the myelomonocytic population. So whether in bone marrow or in spleen, looking at GR1 low expressing cells and high MAC1 expressing cells, which are indicated by the squares, you can see, for example, in the KRAS mutant mice, there is a greater population than in the wild-type mice. Similarly, in the mice bearing the conditional knockout of NF1, there is a greater population of these cells compared to the wild-type, as well as in the mice bearing the mutant SHP2 molecules compared to wild-type. So, and I think this is important because that is very similar to what's seen in the human disease. And in this aspect, I think these murine models are useful in preclinical studies, which we've been talking about.